Even I have a better idea. We can just take this idea, take this meeting, and
Explain
yes,
why. I'd
yes,
like to explain why we're doing this again. So we made a recording a couple of weeks ago. We posted it again, but as everyone observed on this topic, machine learning and science, everyone observed that we kept going off on tangents and we ended up discussing quite obscure questions, forgetting the big ones that we were initially discussing, which is great, which was a lot of
okay,
fun to do. But right now, we'd like to focus on the big question. We'd like to begin, go as far as we can answering the big question, and then get into the some of the other details. And of course, details will arise answering the big question. But if we identify the main theater of debate, that would be the most useful thing to do. So why don't you tell me first? Okay, the main question we're trying to answer is, to what extent is machine learning and more broadly data science a scientific topic? To what extent should science incorporate it, and what parts of it can really be have already risen to the level of science? Yeah. So, what do you think on this topic?
right, right. So if we just look, right, if we just look a little bit in the past, we can see. Let's start from Newton, right? So what did Newton do? He was, it is a story, right? When he was sitting under the tree, the apple falls down, and he discovers gravity. So he made an observation that the apple is falling. So he took one piece of information from all the information available in the universe, and he tried to derive a law. Now, let's say we have different pieces of information and we cluster them together. A cluster in the sense we group them in one place, and then we try to identify if we can derive a law which is very specific to such information. So that is the whole idea behind machine learning or data science in general. So why do we even consider doing this? This is usually, let's say, for business purpose or for scientific research, to predict like what happens next given this information. So that is the whole idea behind data science and machine learning. And some people want to monetize it, some people want to make it state of art and embed with their software. So they all have different reasons. But this is what really happens inside data science. We take X information and we try to predict X plus one.
Hmm. Right. Okay. All right. No, that's very interesting. And actually, I'm glad you took the example of Newton, because I think that's the best place to start. Whenever you talk about science or what are the goals of science, I think Newton is the best place to start, really. I mean, of course,
Right.
there are people who have answered the question, what are the goals of science? What really is science, all over the world and all through
Yes.
the world's history? But Newton has expressed it in very interesting terms. Now,
Yes.
yeah. So actually, now what you said about Newton taking in an observation and building on that, there's a very famous remark that people debate a lot about by Newton. Right? In Latin, it goes hypotheses non fingo, meaning it comes near the end of his great book Principia, and the translation is I frame no hypotheses. Newton was telling that when he was trying to explain, when he came to the question near the end of the book of the origin of gravity. Why do objects attract one another via this gravitational force? And he said, for this, I don't want to come up with any explanations. I frame no hypotheses. And this is a widely debated statement, because people are trying to ask, what did Newton mean by that? Because throughout the book, he framed a lot of hypotheses. He framed the hypothesis that objects exert forces on one another, and these forces can be measured or defined in such and such way. You can always calculate the acceleration of an object and accordingly define the force and also estimate its mass. A lot of hypotheses. Why is it at the end of this that he suddenly said, I frame no hypotheses? And some people say that his idea was, he was trying to say that you should only focus on observations, that all of your theory should basically be a kind of summary of observations, and you should not try to invent anything. But the thing is, the other side of this debate, there was a famous writer in the early 1900s who interviewed Einstein before Einstein was very famous. In fact, just 3 years before he became well known to the world, the non-scientific world. And at that point of time, this man put this question to Einstein. You professor have spoken a lot about inventing ideas, how a scientific theory cannot come from observation alone. It actually has to come first from imagination and then compared with observation. But did not Newton say something opposite to this? Did not Newton say hypotheses non fingo, I make no hypotheses. To which Einstein's reply was, put the emphasis on the last word, hypotheses non fingo, meaning I do not frame any hypotheses. What Newton was saying, according to Einstein, was that I do not need to invent something that is not necessary. I do not need to explain the origin of gravitation because I have no evidence, no measurement, no data to go on that. Instead, I've only invented as much as is necessary. And my inventions are no longer mine. They are actually nature. At first, it was purely my imagination, but after that, it is a picture of nature itself. So that is Einstein's explanation for hypotheses non-fingo. And that's very interesting. So it comes into, so this debate is very broad. On the one hand, there was a person like the author who interviewed Einstein who said, should not observations be everything? Should not the observations be enough? And all theory is just a summary of observations. And on the other hand, there are people like Einstein, all through history, this debate has been going on. The people like Einstein have said, no, observations are not enough. In fact, it begins in our imagination, and then you compare with reality. And that is the idea. So, yeah, what do you think about the role of imagination in science as opposed to the role of observation?
I think we can say those are like two sides of the same coin, or if you take two sides of the same coin, or if you take, let's say, a loop, right? So we do not know where a loop starts, whether it starts at observation or it starts at imagination.
Hmm.
So we do not have a beginning point or an ending point. It's more like two things exist because of each other,
Hmm.
right? If there is no observation, there is no imagination, and without imagination, why do you even care to observe? So these two things, they play hand in hand. But in relation to data science or machine learning, here we have uh, observation. So we have data which is nothing but a result of all the observations, and now we are trying to identify whether this can predict what we can imagine,
Hmm.
right? So whether this can even come close to what we can imagine. So that is the end goal of machine learning. So you look at, like, let's take the classic cats and dogs examples, right? So I'm showing you 100 images of huskies and 100 images of some, let's say, cat breed X. Not, I don't know much about cats. So if given a new image, let's say I'm giving golden retriever or chihuahua, so will it be able to identify? Because it has not imagined, it has just observed.
Hmm.
So will it be able to identify chihuahua? So that is the goal, right? And I cannot say if it's true for the vice versa, because we cannot let machine imagine, right? If we let machine imagine, so I don't know, will it be dangerous, or even it will be possible in the first place? So that is the bias we have as of now.
Okay. All right. Interesting. So yeah, you've spoken a lot of things about a lot of things. So actually, the example of dog was fantastic because very coincidentally, so I spoke about what Einstein said about imagining and then comparing with reality. He had this debate with his friend Maurice Solovine, uh, and Solovine was actually the circumstances in which he met Einstein was very interesting because Solovine was studying philosophy in college, and he found it was too blank, too empty. He wanted something more concrete to go with that philosophy, so he also took some optional scientific subjects, and in that there was a lab subject in which the professor basically said that all science is a summary of data. It's an efficient summary of data. All theory is efficient summary of data. And if new data comes that contradicts the theory, you immediately have to destroy the theory. And so theories are just these temporary constructions summarizing data. But Solomon was not sure about this. So he wanted to learn theory, scientific theory, because and then so he found this advertisement in the paper that had Einstein's name. Einstein was still just a tutor then. He didn't have a job. He was trying to make money giving tuitions, and it was an advertisement for physics lessons. So that's how they met and developed a lifelong friendship. And now the dog example you gave, they actually discussed this about how so very simply put, it was just in one line or so Einstein spoke about it. Think about the difference between the concept dog and the reality. So this is a very interesting dichotomy. What does he mean by the concept of dog? He means by the shape, the logical shape that this concept takes in our mind, right? Because now if you look in a dictionary on the dog or cat or elephant or something like that, these are all standard examples, by the way, in this debate. If you look in a dictionary, you'll find just a line or so describing this animal. It doesn't, there usually no pictures or anything like that. But what the dictionary does basically is give you a hint. And if you observe what the mind proceeds to do with that hint, is it runs wild. It fills up a lot of blank spaces. It extrapolates from the basic narrow hint that the dictionary gave. So the concept dog is such that it can, we know from numerous comic books and fairy tales and all of that, that in our imagination, a dog is a creature that can talk, that might be able to talk or run and fly or do all kinds of things. If you've, I mean, you can think of some, I'm sure there's some comic book in which there's a dog, a comic book like Marmaduke or something, in which the dog is also sensitive to people's feelings. I'm not sure. You can, but in our, that all of that comes straight out of our imagination. But
Right.
yeah, but when we compare it with reality, we find things, you know, completely, slowly, very quickly breaking down. Because, for instance, the dog is not even a coherent object in reality. Its skin cells, its entire body cells change every few years, so that what existed, the material that constituted what we call the dog some years ago, simply doesn't exist at the present moment, because it has grown, it has changed. Most of the cells, that the material that made it up, simply has disappeared in time. So reality, so Einstein basically said that theory and science in general is the comparison of concepts and reality. In fact, Newton said it even better, because Newton in Principia, he gives this thing where he said, when I use these terms, and he gave two examples: space, two or three examples, time, motion. I do not refer to these terms as most people refer to them. Instead, they are, and now I'm not quoting Newton directly, but what he said effectively was, when I use these terms, I'm using them as labels for mathematical concepts. And the attributes, the features of those concepts are different from the features of those same concepts, you know, in other people's minds, in the public imagination. So there is a huge difference between the way a concept forms in our mind, because imagination just happens naturally. In fact, it's a key component of voluntary action, right? Voluntary action is very mysterious. Nobody understands why human beings imagine, why these thoughts just arise automatically out of, without stimulus in our mind. And then we endow the dog with all kinds of properties, but when you compare it with reality, it just doesn't match. So what we do, what a biologist has to do, is they can't study really dog as a concept. They give a certain scientific concept, the label dog, and then try to compare the properties they have, the possible properties that the imagination produces, with the actual properties that appear from experiment. Uh, Maybe I've drifted off too much in the one direction, but it's interesting. That is the basic idea. What Einstein was trying to say to Solving is that for the most part, and we can discuss this, and mainly it has to do with mathematics. Imagination is, a lot of labor is consists in imagination, and consists in logic and mathematics and reasoning. And once you complete all of that labor, there's just a little bit of data needed from the external world. In fact, Einstein even said that the difference between a pure philosopher. Okay, actually, maybe I'll save this quote for later. But tell me what you think. Sorry, I'll save this. I'll explain this later.
No worries. No worries. So I understand. It's an excellent point, by the way, Pitambar. Like the point that you draw out, right? Space time motion.
Hmm.
So again, like earlier we established, right? Even during Newton or pre-Newton, there was certain establishment. Okay, so these laws are like this. But then, as you said, some data comes in and everything drifts, right? So the data causes the drifts in law. So that is one observation that has been happening throughout the history. So we might have some laws today, tomorrow they might just drift away, right? It might not work, like, because we don't have the complete data, and we will never have the complete data, because again, that is why we have these three terms, right? Past, present, future. So again, we cannot catch past, because past is past. We cannot have that information. So we cannot accurately make predictions about the future. So I'll draw out your favorite example, Big Bang, right? So we don't have the exact information, like uh, about the Big Bang, like what happened during Big Bang. Like we have some theories, some mathematics behind it, but again, we don't have the complete information. But in case if we had the complete information at the 0th second of Big Bang, would we be able to predict, like at after that point, let's say after 1 billion years, what will be the state of the universe? Or even now, in this at this point of time, let's say we have some information, some partial information. Will can we predict whether after 10 million years, what will be the state of the universe
Hmm.
with the current information? So such laws. So of course, people can claim, okay, I can predict based upon the current laws, but they don't realize that after this second, the law might change,
Hmm.
and the change is due to the data, or what we call it as entropy, right? So entropy is nothing but the disturbances. So the disturbance changes every instant. So if you don't have the record for n minus one time, how are you going to exact record for n minus one time? How are you going to make an accurate prediction for n plus one? So again, we don't start from zero. We are starting in between when we collect the information, and we are trying to make uh, get the information for the end value. So again, because of lack of information, which is a classic problem in any basic data science problem also, right? We can never have the 100% accuracy of of the law, or of the perfect law, or the perfect model. We can call it as anything. So I hope it makes sense.
Yeah, yeah, no, no, I understand. Okay, so we can, so you feel that the problem is lack of data, and that's why laws are mortal, that they are eventually, theories are mortal, so to speak. Um, is that what you're saying?
Yes. Now let's say Einstein, like with this technology that we have today, will how far his research would have gone? Like he could put his ideas, thoughts into the computers and or into programming. So like he could have done more mathematics or more research than he did like in his time, because he did not have the proper technology. So again, just did not have lack of data. He also had lack of infrastructure, because of which he could not put his thoughts into action, or maybe it affected the pace at which is discovering information, or he's discovering laws, or discovering physics.
Okay,
So
right, right. Okay, all right. So let's think this now. Hold on. Break this down. Okay, so basically here now we have these two viewpoints. I mean, not viewpoints. Let's take a couple of things. One thing is what I'm saying is basically Einstein's suggestion. Okay, maybe now's a good time to give that full remark of Einstein's. So Einstein, so he spoke about metaphysics.
right,
Metaphysics, right? He said his quote was, and it's a lovely remark. It was that from ancient times there have been people who have believed that all about that everything uh, can be discerned about reality. Everything can be understood by purely imaginative thought, by purely constructive thinking. Uh, a scientist is actually one such metaphysician who has been tamed by reality, where he also believes that imagination is everything, but he is willing to budge a little bit and allow a little bit of data from the external world into his imagination. So that is the difference between a scientist and a pure metaphysician. A metaphysician who believes that just pure thought alone can bring about everything. So, I mean, the great classic example. So now you gave entropy. I'm thinking of another. Okay, thermodynamics. Let's think about thermal physics, right? In thermal physics, there's a great law that is Poisson's law, and Poisson's law is put in different formats. This is the general, rough thing, 4 pi rho, and they do different things. It's an example of a differential equation. And let's take a simpler differential equation like the motion. Okay, the apple falling from Newton's tree, right? The apple falling, let's say its initial velocity was 0. The differential equation then would be something like mass into acceleration is the force existing on the being exerted on the apple, right? Now, when you take,
Right.
yeah, the idea here is that the mathematics, which is really just the systematic form of imagination and reasoning, the mathematics gives us everything except two things. To now predict the motion of this apple, we need two pieces of data. Using this equation, we can predict everything except we need two pieces of data: the initial height of the atom, the initial position of the apple, and its initial velocity. And with these two inputs, the mathematics gives us everything. In fact, what it gives us is infinite pieces of data. We can plot as time goes forward, you know, the motion of
Yes, we
the,
can break down.
yeah, we
Yes.
can break it down. It'll go something like this. And that's what's interesting. The thing is, what Einstein was saying was, science has proceeded by taking in very little data and fitting it into a picture that has come out of imagination. Uh, at, and that you keep imagining, you keep creating, you keep going forward like that, and data comes in. It usually doesn't contradict your theory. If you and entropy you mentioned, what that made me think of was the remark that the fact that thermodynamics has not changed in 200 years or so, more than that, in fact, because the laws of thermodynamics have remained the same, uncontradicted for the longest time, because they chose these very powerful mathematical abstractions, which
Right.
made a lot of sense and have still not been, there's still no end in sight. It has stayed static. It's been they've developed mathematics to solve more complex problems related to it, but the basic laws haven't changed. So yeah, that's what I was thinking of. Yeah, go ahead. You're going to say something.
No, no, I'm good. No,
Okay.
you please continue. Yeah.
All right. All right. So then let's go on to the next question. All right. So machine learn, it's a little more specific to machine learning itself. This is
Mhm.
so we'll just answer these two questions, then I'll pause the recording and we'll just discuss some other stuff. I'll ask my friend if
Sure.
he's there, and then we'll go ahead. All right. The next
Just
question.
before just before we begin, just one input.
Yeah.
If that
Yeah. So just before we continue, you
yes,
want to ask? Yeah. Tell something.
yes. So let's say if there was no imagination, sorry, if there was no observation, so I consider observation as data. So if there was no observation, how did imagination come into place?
Yeah. So this is an interesting question about the human mind, right? Whether the human mind develops purely through being shaped from external stimulus, external forces, or there's something else. And there's a very simple test for this. I mean, again, it's a long, great theater of debate, right? Rationalism versus empiricism. That's the name given to the debate. But
Right.
there's a very simple test, right? If you've gone to see a newborn child, and most of us have done that, soon after it's born, and when it's not crying or anything like that, if you move your finger in front of it, in front of its face, it follows your finger. Now, this child has not been fed thousands and millions of pictures of data, images of data, for it to do that, to respond that way to that stimulus. It's been pre-programmed to respond in this particular way to that stimulus. So in a sense, there is a ton that is pre-programmed. In fact, the most powerful studies indicate that within the first year and a half, a child has all of the rudiments of language in its brain already, in before it starts to talk.
So
So there's a lot of
I mean
pre-programming.
that is true. So, but to understand that, we have to go towards Darwin, like how evolution happened, and like how the information has changed in the very existence, in our very existence, right? So at the cell level. So at the cell level, we have been trained just like a model is being trained, as per my understanding. So throughout the, since the Homo sapiens and pre-Homo sapiens, we have faced so many adversities or so many situations, and that information has been embedded in the very basic in the very basic nature that is in a cell. So because of that, we are able to respond to the stimuli. We have developed the understanding. Like you can even observe not just in humans, but also in animals, right? So you can observe like how a dog, like when it's born, it understands like what it has to sniff and why is sniffing essential. Like no one tells the dog go and sniff. That is your, the most strongest sense information. Like it has been developed in such a way through evolution. Like for so many years, um, the evolution happened, and also for so many years, like it was the very life uh, was put under a situation such that it had to develop, and as it procreated, that information was passed on.
Okay. Yeah, go ahead. Go ahead. You're saying more?
Yes. So that is one of the idea behind, like how we are able to adapt so quick. Like if you observe a very smart person, or a very rational person, you'll observe his child is usually rational. And if even if you see his parents, like they happen to be rational. So this information is not something coming out very new. It has been happening for like so many centuries, and that is why the information has been, passed. Sorry, the information has
Yeah.
been passed on, and humans react in certain way. If you just compare a human now and a human, let's say 18,000 years ago, they might not react in the same way. The newborn baby might not react in the same way, because the very encoding is different.
Okay. All right. So this is, but okay. So first of all, yeah, we can talk about that. So you see that regardless of whether it came through, external forces that shaped the human brain this way, the fact
Right.
remains then that when the child is born, it has a brain shaped in a certain way. It's been pre-programmed massively, right?
Right.
So
Right.
so without external observation or external training, the child already has this rich internal structure. So that's what I mean. For example, that's how imagination just arises automatically from within the child without
Yes.
it being
Yes.
fed a lot of data. So
Right. Right.
yeah, so, yeah, you're going to say something. Sorry?
No,
Right.
you are right. Irrespective of what we see outside, it has been programmed at a very subtle level that we don't recognize, or maybe we fail to consider in the equation.
Yeah,
So that's one of the parameter. Yeah.
yeah. And for evolution also, the thing is, right, the idea is that all of these things have come because there are a lot of external forces. And so the current state, human beings as they exist, are the product of, millennia of external molding. But here also, so if you take it is that molding process, it's first of all, it's very mysterious. There's hardly anything that evolutionary scientists are able to answer to the big. There are
Right.
hardly any questions they're able to answer the big questions. But
Right. As I
uh,
mentioned, we have lack of data. That is why we cannot answer for that.
yeah, and also a lack of theory. They don't really have the answers completely. There's so many unsolved problems. But
Right.
the thing is, regardless of that, the thing that had to be molded is a physical system, right? So if you take a simplest physical system, a single particle, that also has these properties. It's pre-programmed to respond to external stimulus, meaning forces in a certain way. So in Newtonian mechanics, a particle, if you just take a simple thing of a particle moving at a slow velocity, much less than speed of light, it is already pre-programmed, first of all, to stay in that velocity for,
Right.
indefinitely, without any change in direction or speed. And it's also pre-programmed that when an external stimulus occurs, when it is exposed to a force, it responds
Right.
according to Newton's second law. That is, it accelerates so that in proportion with that force. So even the simplest physical system has this pre-programming, and there's external stimulus. It knows how it
Mhm.
responds to external stimulus in accordance with this pre-programming. So
Right.
something even so that's true of a single particle, something as complex as a unicellular object.
Right.
It has to be true even then. So if you're going right to the beginning of
So
evolution.
hard to study. Yes.
So yeah, so this is a very interesting theater of debate. I mean, Newton and Einstein are the most famous examples, but there even Galileo also commented on this in very powerful ways. After Newton's passing away, there was a lot of debate based around this. And in fact, Newton's friend John Locke, meaning sometimes friend, sometimes rival,
Yes.
he John Locke actually wrote a lot about this, and Locke came to the conclusion that the entire import of what Newton had done was that all all objects are pre-programmed, and this pre-programming can be thought of as giving those objects a mind. That was his conclusion, that the entire import, the significance of Newton's work was that everything, all these, all matter. In fact, he said matter can no longer be defined, because Newton, the old definition of matter, was demolished with the theory of gravitation. Matter was
Right.
supposed to be, point particles with a certain mass that interact through push and pull. And Newton had
Right.
suddenly shown that objects can interact at a distance without any matter in between them through gravitational
Right.
attraction. So the entire concept of matter is gone. And with that, the concept of body and mind. So Descartes was the one who did this classification in a very eloquent way. Descartes, that is, he said all of nature is divided into these two concerns. Body consists of particles of different masses or weights that interact through push and pull. And
Right.
and then you have mind, and all of nature seems to follow these laws, except the mind, which is too complex. That's what Descartes said. You can't study the mind in terms of these equations of body. But what Locke said Newton's work had done was basically destroy this idea of body, because Newton showed that particles don't seem to interact just through push and pull. In fact, for the most part, they're interacting at a distance through empty space without something in between them. So we can't define
Right.
body. And instead, what Newton did was come up with a mathematical model, which meant that all that remained was mind, that everything was just mind, there was no body.
I mean,
So
what Locke said. I mean, it is one of the theory in quantum physics, I believe, right? If two particles can interact at very even at the large distance, we have a theory for it. So I mean, you're the best person to explain that theory, Pitambar.
this thing, you're saying action at a distance, right?
I would say butterfly
Entanglement.
effect. Like if someone is, yeah, entanglement. If someone is watching, like at layman's level, we call it as butterfly effect, right? A butterfly flapping its wings here might affect tornado somewhere.
Yeah.
So entanglement, like if we consider particles to be um, entangled, like if the origin, the single atom origin, right? There is a theory, I believe. I'm not so good with physics as you are. I'm a data science guy, so you're the best person to explain all these things, Pitambar.
That's fine.
And I believe we should have a podcast just discussing quantum physics. Yeah.
Right. Yeah. No, definitely. So, in fact, yeah. So, yeah, entanglement is the problem of entanglement is considered as a revival of the problem that Newton had, action at a distance. So, Newton's problem was solved in a very effective way in the 1800s by Faraday and Maxwell, and they said that it's not empty space in between the particles. Instead, there is a medium. But like air, that medium is invisible, and that medium is called the electromagnetic field.
Electromagnetic.
So it is
Right.
like a fluid that fills up space, and the particle is not interacting with another particle. Instead, it's interacting with that fluid, and the
Right.
disturbances. Yeah, that fluid carries the disturbances to another particle.
Right.
That's how it is
Right. So
solved.
it's
Yeah,
right. It's a vacuum.
yeah. So
Sure, we should have a special session on this.
yeah,
It would interest anyone who listens to this as well.
yeah, yeah. So it's a very interesting, long problem. I'll pause here now. We'll continue with Anirudh if he's joining, and meantime we'll discuss other stuff.
Yes.
Okay.
Yeah,
Let me
we can
pause.
discuss.
Yeah, resume recording. Great. All right. So finally, I want to ask you about your skepticism relating to neural networks. All right. So you've published a paper recently about regression over neural networks, I think. So yeah, what do you think about neural networks, and why? Yeah, to what extent should we be skeptical and the limits of that? Yeah,
I'm not skeptic about it. I just believe like neural networks are over marketed. Like it's marketing, right?
yeah,
So people market it to sell their course or sell their technology. They call it state of art. I don't know. So
Hmm.
they do that, but again, like how efficient is neural networks?
Hmm.
Because there have been instances, at least in my career, in my profession, right, where I found out linear regression to be superior than neural networks,
Hmm.
and sometimes even custom rules being superior than neural networks, right? So I have had such situations. I don't deny that neural networks are again excellent mechanism to do things, but again, how does it, how well does it fit your data? That is one important thing, right?
Hmm.
uh, so whenever people include neural networks in their project, they fail to consider so many parameters that might that is dependent for creating a model. Like
Yeah.
what is the variance of your data, like how, what is the boundary of your data? They first of all they forget like about the outliers or the boundary value analysis. So and then they see that, oh, their model is performing really well on the trained data, but when it comes to the real time data, it's drifting here and there, like it
Yeah.
doesn't make any sense, like why is it working like this? But then they realize, oh, it's not about the model, it's about the data. So again, neural networks, it might work for some, uh, exclusive data, but not for all data.
Right.
So that is one thing I have seen, and I have experience, and I believe. So I don't sell it to anyone. Like if it's neural network, it's state of art. Even if it's linear regression, even if it's custom rule based, if it solves a problem, it's state of art.
Hmm.
So again, as I would like to put it this way, thinking is state of art. Like if you're able to think and derive, that is the state of art thing.
Exactly.
So yeah.
Yeah.
So yeah, so it's all about simplifying the problem. Neural networks sometimes, not sometimes, many of the times complicates the problem.
Hmm.
So if you're able to simplify a problem, that is more than enough
Yeah.
to achieve good results. Yeah.
Right. That's true. I agree. And in fact, so the neural networks, the entire credibility comes from this theorem called the universal approximation theorem, right? And the problem is, so it says that it can work, that neural networks will give you a good model for just about anything, if you have enough layers, enough nodes, and all of that. And that's the problem, right? At what point do you decide this is just too much data is being, the neural network is taking up too much space, I might as well just keep a lookup table and compress it. Right. That's why
Right.
yeah, I think in fact neural networks and a lot of things in machine learning can be reclassified as probabilistic compression algorithms rather than artificial intelligence or something like that, because if we do that and develop it in that direction, it would make a lot of sense. And the real use, this is what it's used for right now, in a way, compressing that data very efficiently. And yeah,
That is
that's what
true.
it is. Yeah. So, right, this is interesting. Okay, I don't want to keep you longer, but very interesting stuff. And there's so much to talk about in this regard. Let's
Right.
build on this.
I would like to add one thing when it comes to neural networks, right?
Yeah.
So, as you said, neural networks, if we have enough number of nodes, enough number of layers and stuff, we can derive a good model. But to come to that point, right, we need to derive, like, okay, based upon this data, how many nodes I need, what should be the hyperparameters. So many applied data scientists, they fail to do that, and it's not practical to do that, right? Let's say you are getting billions of records or millions of records every day. How
Yeah.
is it practically possible to sit and identify, oh, what's the outlier I got, or what is the new data I got, how is it deviating? So even if you take that everything and try to make some estimation, it would not even be approximate. That is the issue. So
Exactly.
you so that is the issue in applied data science. Again, theoretically, if you have a synthetic data, you can do wonders with neural networks, but
Yeah.
when it comes to real-time data, uh, that is where we are failing. So again, we need to have some sort of custom rules or analysis methods to estimate, and then we can define a neural network and check it out how it's working. So this is where all the MLOps is built around, right? So to identify, like, how is your data drifting, how is your model drifting, and like what parameters are causing this drift. So all this analysis is what a next interesting role and next interesting thing is based upon MLOps, machine learning operations, identifying, like, uh, it's like having a monitor over the machine learning algorithm, which is identifying like what's happening, what is really happening, how is the data and model talking, and if they're talking, I'm sorry, if they're talking, uh, you know, how diplomatic they are, like is data and model. I'm
Right.
just trying to put in layman's terms here, how diplomatic they are, or how, rivalrous they are, because sometimes data is good but model, it's not defined well, then it's going to clash. And it could also be vice versa. So you might have some trade-off like in precision or recall. I mean, not to use such jargons, but uh, again, you will have some trade-off which will not be very pleasant in real time.
Mhm.
So we need to have an estimator that estimates what works well. Again, we have some, actually we really do have some algorithms that can estimate something called as grid search CV, and having such CV. So these estimators are used to identify like what are the best fit parameters, how many nodes, how many inputs, everything. It tries to identify everything. Again, but it's costly. If your data is huge, searching the right parameter is costly. So a lot of trade-offs, a lot of sacrifices, a lot of issues, a lot of headaches. So in midst of this, a data scientist has to make a way. So you can identify like uh, the role of data scientist, like how much he has, how much stress he has to put up when trying to identify all these things.
Yeah, that's right. It's true. And in fact, that's the thing, if you're you have a lookup table. In the old days, they used the word lookup table, and then slowly the phrase evolved to refer to only an array in RAM. So if you had it on disk, it's no longer a lookup table. It's just something else. It's a file containing
Right,
relevant data.
right,
But there were so many different algorithms which you usually sped up using a lookup table, right? Using a cache. You've applied parts of the algorithms to a lot of common data, and you put it into this lookup table. You call it a cache, and you add it to the algorithm. You calculate the time complexity, and it's all sped up. It's much faster. But today,
right,
they're focusing on cutting off that algorithm part, the part without the lookup table, and just focusing on just
right.
adding. That's, I think, everything is stemming from that mistake where nobody is caring about rules and logic anymore, and focusing
Yeah.
more on just trying to fit this on a pattern.
Yes, that there has to be a feedback system. You are right. We need the lookup table acts as a feedback system. It has to exist, but I had no idea about it unless you told me. So if that makes so much sense, Pitambar. Yes.
Yeah. So yeah, we should discuss this in detail.